Good afternoon, everybody. I'm Elahe, coming from Rutgers University. Today, I'm here to talk about bismuth sodium titanate-based piezoelectric ceramics and lead-free high-intensity focused ultrasound transducers. This work was collaborations between Rutgers University, University of Southern California, and Juntong University. The commercial ferroelectric materials are mostly lead-free compositions, and it's because they have high ferroelectric, piezoelectric, and electromechanical properties. Here you can see that the coupling coefficient factor for lead-free materials are between 0.4 and 0.6. However, lead-based compositions have very high coupling factor up to 0.8. And the piezoelectric coefficients for lead-free materials are between 18 to 300. And however, the lead-based compositions shows very high piezoelectric coefficients up to 800. So we could say that under low drive conditions, the lead-free piezoelectrics exhibit inferior properties compared to lead-based materials. But we should consider that under high drive conditions, the performance of materials will change. The figure of merit for high power application is vibration velocity, which is angular resonance frequency and maximum displacements under electric field, and is proportional to electric field mechanical quality factor, coupling coefficient, permittivity, as well as density. In this plot, you can see that the stability of mechanical quality factor rapidly decreases after 0.1 vibration velocity, and is accompanied with heat generation and shifting the resonance frequency, which is not favorable in high-power devices. As a result, the objective of the project was development and characterization of hard bismuth sodium titanate-based piezoelectrics for high-power applications, and evaluation of high-power performance of hard bismuth sodium titanate-based. And the third part of the objective is fabrication and characterization of Bnt-based transducers for therapeutic applications. As explanations, the solid solution of bismuth sodium titanate, bismuth potassium titanate, and bismuth lithium titanate has been chosen to work with. You can see the properties of these compositions, which has been taken from Professor Takanako's work in 2009. These solid solutions, it could make rhombohedral, morphotropic phase boundary, or tetragonal structure. We have chosen the rhombohedral side because it has the highest mechanical quality factor of 400, the piezoelectric coefficients of 95, permittivity of 380, and depolarization temperature of 180. And you can see the chemical formula here. And then we have been trying to enhance the electromechanical properties of these compositions by manganese doping as an acceptor dopant. Here you can see that the mechanical quality factor incredibly increased by doping manganese. At the level of 1.5% manganese doping, the mechanical quality factor in both planar mode and thickness mode reached to the highest value. And at the same amount of manganese doping, we could reach to minimum dielectric constant and minimum dielectric constant, which is favorable for high vibration, for high power applications. So it's motivated me to measure the high power performance of these compositions under high drive conditions. Here you can see that the temperature rise versus vibration velocity. Obviously, by increasing the vibration velocity, the temperature rise. And we could see that by doping manganese, the temperature rise suppressed. And as a definition, the maximum vibration velocity is defined the vibration in which we could raise the temperature up to 20 degrees centigrade. So for undoped ceramics, we have the vibration, the maximum vibration velocity is 0.25. However, for 1% manganese, we could reach up to 0.6 vibration velocity. And in this plot, you can see that by doping manganese, the stability of mechanical quality factor is incredibly enhanced up to 0.45. And then for PCT, for commercial PCT, you can see that the mechanical quality factor is decreased rapidly at around 0.15. So we could say that these compositions can be used in high-power devices such as Hifu transducers. The Hifu high-intensity focused ultrasound transducers is non-invasive treatment, and comparing with other techniques which are guided by X-ray, it doesn't have any, it's non-ionizing radiation, and there is no incisions or stab wounds, which makes the recovery happens very faster. So the amount of the energy deposited on the tissue in Hifu transducers is related to the frequency of the transducers and the intensity of the transducers. So you can see by increasing the frequency, the operating frequency or the intensity, the cavitation probability will increase. In order to design the Hifu transducers, we are looking for material with low frequency design. I mean, we have to design for low frequency, and we need low bandwidth of transducer with high energy ultrasound beam. We need very high mechanical quality factor and low dielectric loss. Until now, most of the Hifu transducers are made with lead-based compositions, but here we choose the lead-free material, bismuth sodium titanate with 1.5% manganese dope. These transducers are single element transducers. We didn't use any backing layer. We didn't use even any kind of focusing technique. So in this table, you can see the properties of the transducers, the frequency of 1, 1.8, 3.35, and 8 megahertz, the thickness and diameter of the transducers. We have been measured the pulse echo response. Obviously, you can see that at 8 megahertz transducers, we have minus 6 dB bandwidth of 21.6. At 5 megahertz, we have minus 6 dB bandwidth of 13.9. And at 1 megahertz transducers, we have very low bandwidth of 11.11%. And then the acoustic characterizations have been done, the acoustic pressure versus peak-to-peak voltage. You could see that the 8 megahertz transducers shows linear response up to 134 volts with a maximum acoustic pressure of 1.77 megapascal and intensity of 104 watt per square centimeter. The 5 megahertz transducers shows linearity up to 109 volts with the maximum acoustic pressure of 2.7 and intensity of 258 watt per square centimeter. And the 3.3 megahertz transducers shows nonlinearity after 99 volts, which it has the maximum acoustic pressure of 3 and intensity of 330. And then here you can see the two-dimensional distribution of acoustic pressure field and acoustic intensity were aligned the z-axis for 5 megahertz transducers. The 5 megahertz transducers get to the acoustic pressure and the intensity for this transducer reach to the maximum amount at 95, which is the natural focal point because we didn't use any lenses. And then for 1.8 megahertz transducers, you can see that the negative pressure is saturated at 73 volts, and the nonlinearity has happened after 102 volts, and the mechanical index is 1.5. The 3.3 megahertz transducers has nonlinearity after 90 volts, and the negative peak saturation occurs at 78 volts with mechanical index of 1.09. The acoustic pressure measurement versus frequency for 3.3 megahertz shows that we reached to the maximum pressure at exactly at 3.3 megahertz transducers. Sorry, megapascal. And then we measure the acoustic pressure field and acoustic intensity along the z-axis for 3.3 megahertz and 1 megahertz transducers. You can see that the maximum intensity for 3 megahertz transducers is 300 watts per square centimeters, and in 1 megahertz transducers we could reach to 3,000 watt per square centimeters, which is desirable for Hifu transducers. And as a conclusion, we developed manganese-doped ceramics for high-power applications. Lead-free ceramics show superior high-power performance compared to commercial hard PZT in the term of lower heat generation and higher stability of mechanical quality factor. And then we have been measured the bandwidth for the Hifu transducers. It's 11.11, 30.9, and 21.60% respectively. And Hifu transducers with center frequency of 3.35 and 8 megahertz shows linear response up to 99, 109, and 130 volts, in which maximum peak acoustic pressure of 3, 2.78, and 1.8 megapascal were achieved. Thank you for your attention.